Good day class. We will be embarking on understanding fundamentals of AC circuits with this week's series of lecture videos. In this lecture, we will try to derive expressions to represent resistance, inductance and capacitance in AC analysis. We will first define complex impedance and its equivalency in DC analysis, then derive the expression for resistance, inductance and capacitance in an AC circuit, and finally identify a general representation for load comprising of resistance, capacitance and inductance. We have the Ohm's law, which relates voltage and current to the resistance of a component in a DC system as follows. Resistance is defined as the voltage V divided by the current I. We can define a similar parameter for use in AC system. This is called impedance and can be considered as complex resistance. Similar to the DC system, we can define the impedance as the voltage phasor V divided by the current phasor I. This relation is the Ohm's law equivalent for AC system. Since we have defined impedance, let us see how a resistor is represented in an AC circuit. Consider a resistor with resistance R. A voltage VR equal to Vm cos omega t is applied across the resistance. The current through the resistor is derived as I of t is equal to VR of t divided by R is equal to Vm cos omega t divided by R. The current is Vm by R into cos omega t. The voltage phasor here is Vm by root 2 at an angle of 0 degrees, while the current phasor is Vm by root 2 R at an angle of 0 degrees. Thus, the impedance of a resistor or the resistive impedance is defined as the voltage phasor divided by the current phasor, that is R at an angle 0 degrees or simply R. If we draw the phasors for voltage and current, we notice that for resistive elements, VR and IR are in phase with each other. Next, we see how an inductor is represented in an AC circuit. Consider an inductor with inductance L. A voltage VL equal to Vm cos omega t is applied across the inductor. The voltage across the inductor is also given by VL is equal to L dIL by dt. Thus, we can find the inductor current by integrating both sides of this equation. This gives us the current as Vm divided by omega L times sin omega t. Rewriting this in cosine form, we get IL of t is equal to Vm by omega L times cos omega t minus 90 degrees. The voltage phasor is defined as Vm by root 2 at an angle 0 degrees, while the current phasor is Vm by root 2 omega L at an angle of minus 90 degrees. Thus, the impedance of an inductor or the inductive impedance is defined as the voltage phasor divided by the current phasor, which is omega L at an angle of 90 degrees, which is also equal to j omega L. If we draw the phasors for voltage and current, we notice that for inductive elements VL and IL are not in phase with each other. Rather, IL is lagging VL by 90 degrees. Finally, we see how a capacitor is represented in an AC circuit. Consider a capacitor with capacitance C. A voltage Vc is equal to Vm cos omega t is applied across the capacitor. The current through the capacitor is given by the expression C dVc by dt. This gives us the current as Vm times omega c times minus sin omega t. Rewriting this in cosine form, we get Ic of t is equal to Vm into omega c times cos omega t plus 90 degrees. The voltage phasor is defined as Vm by root 2 at an angle 0 degrees, while the current phasor is Vm omega c divided by root 2 at an angle of plus 90 degrees. Thus, the impedance of a capacitor or the capacitive impedance is defined as the voltage phasor divided by the current phasor, which is 1 by omega c at an angle of minus 90 degrees, which is equal to minus j by omega c, as minus 90 degrees corresponds to minus j or 1 by j omega c. If we draw the phasors for voltage and current, we notice that for capacitive elements, Vc and Ic are not in phase with each other. Rather, Ic is leading Vc by 90 degrees. Let us summarize the representations in the following table. For all these elements, the voltage phasor is Vm by root 2 at an angle of 0 degrees. For the resistor, the current phasor is Vm by root 2 R and the resistive impedance is R at an angle 0 degrees or R. For the inductor, the current phasor is Vm by root 2 omega L at an angle of minus 90 degrees and the inductive impedance is omega L at an angle of 90 degrees or j omega L. For the capacitor, the current phasor is Vm omega C divided by root 2 at an angle of plus 90 degrees and the capacitive impedance is 1 by omega C at an angle of minus 90 degrees or 1 by j omega C. We looked at individual R, L and C in isolation. Let us take a combination of two of the elements. Impedances, like resistances, add up when connected in series. Here we have an RL load. Here the total impedance is the resistive impedance plus the inductive impedance, or we can say that the complex impedance ZRL is equal to R plus j omega L. Here we have an RC load. Here the total impedance is the resistive impedance plus the capacitive impedance, or we can say that the complex impedance is ZRC is equal to R plus 1 by j omega C or R minus j by omega C. We have come to the end of this lecture. In this lecture, we examined the concept of complex impedance and derived the representations for resistor, inductor and capacitor in an AC system. Thank you.